Should I take off my mask?
Yeah, maybe up to you. It's okay.
Okay.
Oh, it's already on? Okay. 시작할까? Right, thanks for coming. So today we're pleased to have a Cheolwon Heo from Sungkyunkwan University. And we talk about matroid-homomorphism, the complexities. Please.
Thank you for the welcoming introduction. Today I talk about matroid-homomorphism. It's a kind of generalization of graph homomorphism, but we talk homomorphisms between only binary matrix. So let me start with the graph homomorphism citation. So, we say G home. Function from vertices of G to vertices of H that preserving adjacency. That means for every H in G, FV is also an edge of H. So there are, let me give an example. So we denote this by arrow with sub G here. Let me represent this function by coloring. Here, so let's say F send this vertex to red vertex, and this one to blue one, and so on. So this function is a graph homomorphism because for this edge, this vertex goes to red one, this goes to blue one, then let's say U is here, V is here, then FV and FV should be this edge of H. So this is the graph homomorphism. So as you can notice here, actually, this graph homomorphism impact three coloring of G. So in general, if there is a graph homomorphism from G to Kn, this implies that G has n proper coloring. And another easy remark is there is a graph homomorphism from Kn to Km if and only if A is same as M. So it's easy to see because if this is true, this means Kn is n colorable, and that means n is less than n. And this implies that Kn is a subgroup of Kn, subgraph, sorry. And this means there is a graph homomorphism from Kn to Kn. So they are equivalent. I don't know what's the best way to use this.
You're the first one, sorry.
So with this, we can consider the following problem. So H is a given graph. Let's say G here.
조금만 오른쪽으로 가보시면 유튜브에서 보일 것 같아요.
어떻게 해야 되죠?
트래킹 안 켠 거.
그 자동으로 따라가던데.
하고 계시면 될 것 같습니다. 진짜
네.
아니, 어떻게 하나요?
수동으로 할 거면 그냥 여기다 계속 할까요?
돼 있는데 이게 안 따라가네요.
아니 밑에 트래킹 버튼 있잖아.
네, 일단 계속.
예.
So instances are graph G. And this is a program, and we want to know if there is a graph homomorphism from G to H. So this is yes if there is a graph homomorphism, and no otherwise. And there is a nice theorem by Hel and there are only two outcomes in terms of complexity. So this is in P if so this kind of theorem is called complexity dichotomy. Okay, so how can you prove this? So for P part is to C, because if H has a loop, then we can consider a graph homomorphism from G to H that sends every edge to the loop. I mean this vertex with a loop. So let's say for all u. Then for every edge we have loop twice. For every edge UV. So let's say U1, U2 are adjacent, then it sends to the same vertex V. So F U1, F U2 are adjacent because there's a loop on this vertex. For MPC part, for bipartite, this one is.
I don't understand the loop part. That's trivial, right? You can just map everything to the loop vertex.
Yeah, exactly.
Oh,
Right.
okay.
So for
loop means you just have at least one loop, right?
at least one loop, yes.
Okay.
For bipartite, it depends on G to be bipartite or not. So if G is bipartite, we send every vertex. We have two. We have a partition, bipartition of G. Then we send one. So let's say H has an edge. So this is edge in edge. So and G has a bipartition. Let's say A and B. And we send these vertices to here and these vertices to here. That gives a homomorphism. And there's a polynomial-time algorithm to recognize if a graph is bipartite or not. So we simply take the spanning tree of the graph, and whenever we add an edge, we check the fundamental cycle and check if it's even length or not.
So that condition is about G is whether or not bipartite, right?
Yes. So it's in P.
But why we need here if A is looped or
And we don't know if there is a homomorphism or not.
okay, yeah. Got it. Thank you.
Oh, there's no clock in this room. For MPC part, we will show that A3 edge. So this inequality means that every instance of this problem can be reduced to an instance of this problem in polynomial time. So this is the way to prove. This is well known for MPC, and this implies that this one is NP complete when H is loopless non-bipartite. So now we want to generalize this definition for matroid. So let's say M. So here we have binary matroid. And let's say M to N. Is a function f from ground set of M to ground set of N, such that for every circuit C of M, symmetric difference of Fe is a cycle of N. Here I mean by cycle a disjoint union of circuits. And we denote this by m to n together with this index n here. So one easy remark is that if G to H, if there's a graph homomorphism, then there is a matrix homomorphism between this binary matrix. So F is given by this. Then let's say this is red, 0, blue. Then how can you build a matrix homomorphism from this graph homomorphism? This edge is red dot and blue dot, so that means red to blue. So it's colored by red, so we color this red. Red, blue, same. Blue, yellow means blue. And the same thing. And it's easy to see that this is a matrix homomorphism because for any circuit of this matroid, we can consider the closed walk of this circuit, and then that become a closed walk in this graph. So we can see that. So this means we choose the only edges that appear odd number of times. So, for example, this cycle, this circuit goes to the blue, red, blue, yellow. So this becomes blue, red.
So that becomes the empty set, right?
Yeah.
So
Yeah, because of symmetric difference.
And then blue. Right? Yeah, exactly.
and the empty set you also allow as a cycle because it's the empty.
Right.
distribution.
Empty distribution. Yes.
I see.
Now we can see the same problem. So I will use this as well. So I'm here. Binary matrix n. And this one is, yes, if there's a matrix homomorphism from n to n and no otherwise. And we prove the analogous theorem with this homomorphism. So actually the result is the same. And I will give a simple idea to prove this one.
So what does it mean the matroid is looped?
There's a loop. So for binary matrix, you can consider the binary representation. So as a 0-1 matrix, then there's all 0 vector. That's a loop of the matrix. So if there's a column with all 0, then it's looped. Otherwise, not.
Bipartite?
Means every circuit has even cardinality. There's no odd circuit. So this is the key idea. So for graph G, define G hat be a graph obtained from G by adding a vertex and drawing every vertex from V star to any vertex in G. So it should be matroid of G hat and matroid of K3. I will obvious some terminology. So for graphs, we will consider graphing matroid represented by this graph. So this idea is pretty nice because we know the relation between graph homomorphism and matroid homomorphism. So I will prove it by an example. That's not a formal proof, but so we know that there is a graph homomorphism if only if it's 3 colorable. So for example, we have this 3 coloring. So let me define the matroid homomorphism for this case. So this one is red, so we color V star and this vertex by red. And this vertex is colored by yellow, we color this edge by yellow, and so on. For G, we color it by the third one in each fundamental cycle. So for this cycle, we have red and yellow, so we color this by blue, red, yellow here, and here as red, and then blue. The thing is, these cycles are fundamental cycles, and it's correct to be matroid homomorphism. So every cycle, every triangle has 3 colors, so it's a circuit of this graph. And then the last, for the last circuit, we get it for free. And the converse is very similar. And we want to generalize this idea. We want to develop this idea to solve the theorem 2. So let's say for a graph G, we define GK hat this is the graph from G by adding V star and K passes to each vertex in G. And for a binary matrix N, HK of N is a graph. It's a simple graph defined as follows. So vertex set is a ground set of N. So let's say W is the vertex of this graph. It's a subset of ground set of N. And its cardinality is almost K, and K minus this cardinality is even. And for H set, W1 and W2 are adjacent in this graph if only if there is some element E such that W1 symmetric difference with W2 with this E is a cycle of N. Then we have a similar lemma and binary matrix. Okay. So we can ignore this one. If there is a graph homomorphism from G to HK N, if only if GK hat to N here. So I will skip the proof is very similar to this one.
So basically, you look at the all subsets of size
almost
K with certain parity,
Right.
and then edges are describing when you make a cycle.
Let me explain briefly that.
Can I ask one question?
Yeah, sure.
So you described the construction this HK, which
Yes.
convert binary matroid into a graph. So suppose between two binary matroids, I have a matroid homomorphism. So in your definition, does that imply your HK of N and HK of N prime? There is a graph homomorphism between the two?
Could you say that?
So HK is an operator on binary matroid,
Right.
which converts binary matroid into a graph.
Right.
So I'm wondering whether that preserves matroid homomorphism. So if we have a binary matroid, and then there is a matroid homomorphism between the two.
Okay, let's say n to n.
Yes. Then now suppose I apply HK on both sides. Maybe yes, like that. Then there is some standard way of constructing homomorphism between the two.
Graph homomorphism?
Yes.
I don't know.
I'm asking this because your stuff looks a bit like what people call adjoint in the category theory. So just a bit like a inverse with each other. But
I never thought about that. Maybe it's true. I don't know. Okay. So let's say that there is a graph homomorphism from G to HKN. So we can color each vertex with an element of HKN. So there are some W1, W2. And this is our GK hat. And we color this set. We use this set to color this path. So this is at most K subset with the same parity with K. We color this maybe here W1. So if it's less than K, we just add same color here to hit the color K. So they are cancelled out anyway, so it doesn't matter.
I see.
So and this gives a proper matrix homomorphism. So for this edge, let's say that W1 and W2 or W3. So this is an edge. So there is a edge FW1, FW3. That means there is an element of n such that W1, W2, and E form a cycle, and we use that E here to color this one. So and then we use the same argument. So for every fundamental cycles we have a correct coloring, and the other cycles we get it for free. So for theorem 2, let me remind. Bipeptide. So actually the proof for P part is the same as graph homomorphism. So let's see this part. So let's say n is loopless and non-bipeptide. Then there is k, integer k, such that n has a 2k plus 1 of circuit of length 2k plus 1. And by this lemma, we know that for every G, these two are equivalent. And the thing is, we have a cycle or a circuit in this graph because let's say that this cycle is E1, E2 up to E2k plus 1. Let's say when k is 2. So maybe it's easier to understand. So we have 5 cycle here, 5 circuit in this matrix, and then in H2n we have this cycle. So it's 1, 2, 3, 4, 5, 1, 2, 3, and 4, 5. So there's an edge between 1, 2, and 3, 4 because we know 1, 2 plus 3, 4 plus 5 is the circuit of n. So this is also 2k plus 1 circuit. And by the theorem 1, which is proven by Heo and Leslie, this is NP-complete. So we know the homomorphism problem for n is also NP-complete in this case. So this is a kind of side story. So we know that if there's a graph homomorphism from G to H, then there is a matroid-homomorphism from G to H. But the converse is not true in general. And the well-known example is K4 to K3. So there's no homomorphism because K4 is not 3-colorable, but there's matroid homomorphism. We can see this by the lemma 4 because H1 K3 is K3. So if we use this lemma, then this one with K equal to 1, G equal to K3, let me write. So G is K3, then G1 head is still is a K4 because with K3 we add vertex and join 3 edges. So it's K4 and this is still K3 and this is K3. But we know there's a graph homomorphism, trivially, so there's a matroid homomorphism. And actually, that's the unique example with the counterexample. So, actually, we proved that if Kn, if there is a matroid homomorphism from Kn to Kn, then either n is less than m or that example. So it's kind of interesting because for graph matroid we have only this. So I think we can skip this direction. And suppose there's a matrix homomorphism from Kn to Kn, and n is bigger than n. Then we use this lemma for with this should be Kn, so G is Kn minus 1 and n is Kn. Then we have I think it should be 1. Right. And because we assume there's a matrix homomorphism, so we get this. And so here is the fact. You can check later. So H1 Km so largest click of this graph is Km when m is 3, otherwise m minus 1. So actually for m equal to 3, h1 of k3 is k3, and for k4, let's say, so this is k4, and how can you draw this? So it's so 1, 2, 3, 4. Okay. We should label the edges. So it's symmetry. So let's say that let's see the neighbors of 1. So So there's an edge between 1 and 2 because 1 through 4 is a triangle. So it's 2, 4.
Except 5.
Yeah, except 5. And there's an edge here. Two with a 4, 5, 1, 3. 4, 5, 1, 3. 3, 6, 4, 6, something like this. So if you consider the clip containing 1, then you can see that K3 is the maximum. So where are we? So this happens when m is exactly 3 and m minus 1 is exactly 3. So if n is 4, then this cannot happen because m minus 1 is n is m. So it should be 3, and then if n is 5, then it's bigger than 3, so it cannot happen. Should I skip the one literature? So there was some previous proven lemma by 4 people. So they proved that this, but our theorem is much stronger than this. So I have 10 minutes, so let me talk about variations of this problem. So when you have homomorphism, we can consider some variations. So first one is list. So its instance is matrix n together with the list. And we want to decide, yes, if there is a matrix homomorphism from n to n such that f of e is in the list. So B and no otherwise. So it's kind of list coloring problem. And we also proved the dichotomy theorem for that problem. there are only 4 cases. So it's a loop, an edge, this one. So pretty much this is hard for most cases. The other variation is extension problem.
So if n is the cycle matroid of one of these graphs, or
Yeah, psychometry of this graph.
okay.
For this problem, our instances are binary matrix M together with list. Now it's pre-colored or not, so that means it has cardinality 1, which means pre-colored, or we have full offshot. And decision is the same as list home. It's a special type of list home problem. And we have a theorem for that as well. Either loop projective geometry or affine geometry. So one easy way to think about this. This is vector space. So, for example, with rank 3, we have every possible vectors. This is one example. And for affine geometry, we have columns with odd number of ones. So it's 0, 1, 0. Yeah. So, okay, I'll stop here today. Thank you for listening.
Right, any questions? So I have one question, a couple of questions. One is, can you tell us about the origin of this concept, the homomorphism for matroid?
What do you mean, original?
Like, I mean, who invented this matroid homomorphism? Was it in your paper, or does it appear in an earlier?
We tried to find our own definition, but it turns out it's the same as previous definitions. One of previous definitions.
Yeah, so I was wondering who did it. My second question is, if you have a homomorphism, then can you say something about the dual matrix? Like if you have a homomorphism from M to N, then does it follow that the dual goes to the dual, or?
I don't know. I have not thought about that.
Uh-huh.
But that's an interesting question. What about graph homomorphism? Can you say something about dual? If it's planar.
Well, I don't know. Because for graphs, it's vertices are mapped to vertices, but here it's edges to edges, so there might be a sensible way of seeing it by dual matrix. But
Yeah, but we can start with graph homomorphism, because if there is one, then there is a matrix homomorphism as well.
uh-huh.
In my opinion, if we can understand it as some from to chain group, binary chain group to chain group, then maybe just
Yeah. And how far can you extend this concept? Is there a sensible way of defining homomorphism for like non-binary matrix?
We consider about circuit preserving map, but if it's non-bipartite, but it's not non-binary, then actually proving something is in P is very hard in general. So, for example, for ternary matrix, I don't know how to prove. There's a polynomial-time algorithm for ternary homomorphism.
so. For the you means that case of the binary, you map circuit to the cycle, but when you consider ternary or something else, then you only consider the circuit to circuit, or
Yeah, so because we cannot talk about cycle for non-binary matrix.
Alright, any other questions? Lucky you don't have any. Alright, okay, if not, let's thank the speaker again.